Okay, just 1 second. Almost ready to. So, our next speaker, Krystian, who speaks on inequalities for the multicolor restricted partition function. So please go ahead.
Thank you very much for introducing me. It's a great pleasure to me to give a talk about my research during the combinatorial and deep number theory conference this year. And today I would like to say a few words about the multicolor restricted partition function and some inequalities related to this object. However, before we go to the main part of my talk, let me recall the most basic objects connected with the theory of partitions. Namely, by a partition lambda of a non-negative integer n, we mean each non-increasing sequence of positive integers lambda n 1 up to lambda r, such that the sum of this element equals n. The elements lambda I are called the parts of the partition lambda. And now, if you have a definition of a partition, one can ask how many such partitions do there exist for a given parameter n. In other words, we may define a function which counts the number of partitions of n, and this function is called the partition function. Of course, this function can be extended for all integers n simply by putting 0 if n is negative. And it is also worth mentioning that p of 0 equals 1 because there is only one partition, namely the empty sequence. So, for example, we have 7 partitions of 5 because we have the following possibilities to represent 5 as sums of positive integers. Good. So the first part of my talk is devoted to the Bassenrod-Ono inequality. Namely, in 2016, Bassenrod and Ono showed that the partition function satisfies the following inequality for all positive integers a and b, which satisfies the following condition. Actually, their theorem, their result, has initiated a great research related to discovering similar inequalities for another variations of the partition function. For example, for the so-called k-regular partition function. That is, on the other hand, the partition function which counts only those partitions of n which parts are not congruent to 0 modulo k. And for more other variation of the partition function. Their proof is based on the analytic behavior of the partition function. They used the theorem of Lemo. More about this in a few minutes, but it is also worth saying that there are, as far as I know, there are another 2 proofs of this fact. Namely, Al-Nasji, Gagola, and Munagi proved this theorem in a combinatorial manner, and more recently, Hyman and Hauser showed this inequality by induction. So what about the original proof? The original proof, as I previously mentioned, takes advantage of the Lemo Theorem from 1939, which says something about the asymptotic behavior of the partition function. And from this fact, Bassenrod and Ono were able to deduce the lower and the upper bound for the partition function. And now the idea of the proof is simple. Well, we bound from below P of A times P of B, and from above P of A plus B, and check under what condition of A and B the following inequality holds. And it turns out that after some manipulations of this inequality, we can obtain that it is satisfied for almost all numbers A and B, and in the remaining cases, we check the validity of the theorem one by one. Good. So what about the Bassenrod-Ono type inequality for the multicolor restricted partition function. And what exactly is a multicolor restricted partition function? So let me define at the beginning the multicolor restricted partition. In order to do that, we need have a positive integer k and a weakly increasing sequence of positive integers, curly a. It can be, it doesn't need to be infinite sequence. This sequence must be of length at least k. So it is not necessary to have this infinite sequence here. And then by a multicolor restricted partition lambda, we mean each partition such that the parts of the partition belong to the multiset which consists of the first k elements of the sequence curly a. I said the multiset because in fact it may happen that, for instance, a1 equals a2, but we distinguish this element in some way. Therefore, in order to omit the ambiguity, we need to further assume that two multicolor restricted partitions are considered the same if they differ only in the order of their parts. So if we have this definition, now we can define also the multicolor restricted partition function, which of course counts the number of multicolor restricted partitions. Great, so let us take a look on a basic example. Let us consider the sequence of consecutive positive integers such that each number j appears in j distinct colors. If we take, for instance, k equals 7, then for a given parameter n, we look only on those partitions of n which parts belong to the multiset which consists of blue, the 1 in blue, 2 in blue, and up to the 4 in blue. So this is the multiset. And in particular, if n equals 5, then the value of the multicolor restricted partition function in this case equals 16, because we have the following possibilities. The theorem I was able to deduce, which is related to the Bassenrod-Ono inequality, says that if we assume that k is at least 2 and curly a is a weakly increasing sequence of positive integers with the additional assumption that the greatest common divisor of the first k elements of this sequence equals 1, then the Bassenrod-Ono inequality for the multicolor partition function holds for all a and b strictly larger than the following number. And actually this proof has some advantages and some disadvantages. The main disadvantage of this theorem is that this demand for a and b is a very strong assumption. And in many cases, it turns out that it is enough to take much more smaller number a and b in order to obtain this inequality. However, on the other hand, the main advantage of this theorem is that it can be successfully applied for a wide family of integer sequences. And moreover, we cannot extend this family in a sense that we cannot leave any of the assumption appearing in the statement. For example, if we assume that the greatest common divisor is greater than 1, then this inequality cannot hold. What about the proof? My proof is also based on the analytic behavior of the function p of nk. Namely, I took advantage of theorem of Neto and Polishigo from 1920s, which states that the restricted partition function behaves in the following way. So it is like a polynomial with the degree k-1. Actually, the restricted partition, the multicolor restricted partition function is not the polynomial, but it is a quasi-polynomial. So it can takes different values on, so it can be defined by different polynomials on some residue class, on different residue class modulo the least common multiple of a1 up to ak. So with this theorem, actually this theorem was the proof of this theorem Duetto-Netto and Poliszygo was obtained by the partial fraction decomposition of the generating function related to the function P of nk. And it is also worth mentioning that there is a very nice proof of this fact by induction due to Professor Nathanson. And from this theorem, the idea is quite easy. We want to bound the function P of nk from above and from below by the following expressions. And once again, we observe that if k grows, then this bounds became more and more inaccurate. So this is the problem. And how can we obtain the value of the constant c? In order to do that, we may apply, for instance, the theorem of Chimpanzee-Nikolaev from 2018, which gives us an explicit form of the multicolor restricted partition function. It is quite complicated but we can find some bounds for the appropriate values of the values of the quasi-polynomial P of nk. Good. So that is actually the theorem. And now if we have this bounds, then we actually do the same trick as in the case of the original proof of the Bassenrod-Ono inequality, and obtain the theorem from the one of the previous slides. Good. So now I would like to say a few words about a bit more complicated issue, namely something about the log concavity of the restricted partition function. Let me recall that the sequence of real numbers is log concave if it satisfies the following condition for all n greater or equal than 2. In fact, we can demand that at least this inequality can holds for sufficiently large values of n. In 2015, De Salvo and Pak reproved the theorem of Nicholas from 1978 that the classical partition function is log concave. In fact, this theorem was a motivation for the Bassenrod-Ono type, for the Bassenrod-Ono inequality, and as in the case of the Bassenrod-Ono inequality, this theorem has initiated a great research related to investigating similar inequalities for another variations of the partition function. So what about the log concavity for the multicolor restricted partition function? This is a quite intriguing question, and it's a quite difficult task. And before we give an explicit criterion, let us take a look on a few examples. In order to make our notes a bit more transparent, let us put that capital delta equals the following difference. So in particular, if the value of the function capital delta is positive for sufficiently large values of n, then the corresponding multicolor restricted partition function is log concave. And for example, if we take a sequence of consecutive powers of 2s, then the partition, then in this case, we deal with the so-called restricted binary partition function. And if we fix k, for example, k equals 5, and check the values of the function capital delta for n between 2 and 100, then it turns out that sometimes the value is positive, sometimes the value is negative. And if you replace if you replace 100 by 1000, then once again we see that sometimes this value is positive, sometimes is negative. And actually, if we replace 5 by any other positive integer k greater or equal than 2, then we obtain very similar graphs. It is because it is quite easy to observe that if n is odd, then the value of the restricted binary partition function of n minus 1k equals the value of this number. And on the other hand, this is strictly smaller than the value of p curly b of n plus 1k. So we cannot have the log concave. So the restricted binary partition function cannot be log concave. And in particular, if we replace 2 by any other positive integer m greater or equal than 2, then, and consider the sequence of consecutive powers of m, then we also obtain that this, in this case, restricted MRA partition function cannot be log concave. Good, so now let us take a look on the example we dealt with before. So this is a sequence of consecutive positive integers. And if we take k between 2 and 4, then it seems that once again we cannot tell anything about the log concavity, or rather we can say that the restricted MRA partition function is not log concave in these cases. However, if we take any k greater or equal than 5, then it's practically surprisingly it seems that we have the multicolor restricted partition function is log concave. So the first question is, what's the difference between this sequence and the sequence before? But we will see it in a few moments. Because let us now take a bit more interesting sequence. Namely, let us consider the sequence which consists of 5 2's and only with 3's. So we have only 2 numbers in the sequence, but in distinct colors. And now if k is between 1 and 6, we see that it seems that the restricted the multicolor restricted partition function cannot be log concave. The similar observation can be made if k equals 7, but surprisingly, if we assume that k is at least 8, then we obtain that in fact the corresponding multicolor restricted partition function is log concave for sufficiently large values of n. So what about the theorem? The theorem says that if we have a weakly increasing sequence of positive integers, then we have 2 cases. If k is either 2 or 3, then we need to assume that a1 equals ak equals 1, and in that situation we obtain the log concavity for all n greater or equal than 2. It is quite easy to verify. And on the other hand, if k is greater or equal than 4, then we need to assume that the greatest common divisor of A, where R is any k minus 2 multisubset of the following multiset, then we obtain the log concavity of the sequence for all n strictly greater or equal than the following number. So once again, there are some advantages of this theorem and some disadvantages. The main disadvantage is the value of this number. It is once again much more larger than in many cases is needed. However, the main advantages is that we cannot extend this theorem further, in a sense that we cannot add any sequence of we cannot leave any of the assumption and obtain the log concavity of the multicolor restricted partition function. In other words, this without any of this demands, the log concavity cannot hold for the multicolor restricted partition function. And the theorem is once again in analytic manner. And in order to obtain this fact, I took advantage of the Almqvist theorem or Beck theorem, which gives us a bit more accurate estimation for the multicolor restricted partition function. Of course, we need some additional assumption on the multiset A1 up to AK, but after that, we can say something more about the multicolor partition function. And the value sigma I appearing here in this theorem are defined by the following formula. And now, in our case, it is enough to assume that every k-2 multi-subset of this multiset is coprime. And if you have this, then the first two coefficient of the multicolor partition function are fixed, and it is enough to bound the fourth coefficient, which appears next to the n to the power k-4. And in order to do that, once again, we can apply the theorem of Chimfaz and Nicolas and do the same trick as before. If we do that, then we obtain the theorem from the previous slide. However, this approach can be also successfully utilized in if we would like to deal with another inequalities related to the multicolor restricted partition function. For example, if we want to check under what condition on the multiset A1 up to AK the following inequality holds. Then if we assume that k equals 5, then it is actually the same assumption as in the theorem related to the log concavity of the multicolor restricted partition function. If k equals 4, then we need to assume, and we should assume that n is at least equal to the following number. And of course, we can also deal with the case in which curly A is a sequence which consists only of ones. In that case, it can be quite easily verified that this inequality holds for all k greater than 3 and n greater or equal than k over k-2. And it is worth observing, it is worth mentioning here that the exponent appearing in the denominator here cannot be replaced by any smaller exponent. So in some sense, it is the best one in this for the multicolor restricted partition function. The thing we can do is we can replace 1 by some larger number. I do not remember how large this number can be, but it might be slightly larger than 1. Good. So a few words about another consequences, about some another inequalities which can be deduced from our approach. Namely, we can consider the strong long concavity of the multicolor restricted partition function, in which we assume that we have a fixed positive integer m, and we consider under what condition on the multiset, actually on K and the sequence curly A, the following inequality holds. And it turns out that it also holds if we assume that every k-2 multi-subset is coprime, so it is almost the same as in the case of the log concavity. However, the computations are slightly a little bit more complicated, but not a lot. And also one can deal with the following problem, and it also suffices to assume that every k-2 multi-subset of the multiset A1 up to AK is coprime. Of course, we have another assumption on the values of the parameter n, but the reasoning stays the same actually. Great. We can also investigate the log concavity of the following sequence. And as far as I know, it holds with this approach. This is log concave for all alpha greater or equal than 1. And I strongly believe that it also can be shown that it is also log concave for alpha strictly larger than 0. And also with the assumption that every k-2 multi-subset is coprime. Further, we can also deal with the so-called the log balancedness of the multicolor restricted partition function. That is the question when the following sequence is log concave. And in this case, it is enough to assume that every k-1 multi-subset of A1 up to AK is co-prime. And actually, there are many more intriguing questions about, for example, higher order Turan inequalities. This is actually the second order Turan inequality. And if we replace Cn by the corresponding value of the multicolor restricted partition function, then this inequality holds if we assume that every k-6 multi-subset is co-prime. We can also deal with the higher order log concavity. That is the case in which we define another sequences qi of n recursively by the following formulas. And we say that in this case, P of nk is asymptotically R log concave if it satisfies the following conditions. So if there exists some capital M such that all the values of the sequences are non-negative for the values greater or equal than M. And up to this day, I was only able to show that the sequence P of nk is 2 log concave with the same assumption as in the second Turan inequality, namely at every k-6 multi-subset is of A1 up to AK is co-prime. So I still have a lot of work to do, and maybe next time we meet, I will be able to perform my results. So that is everything I prepared for today. Thank you very much for your attention.
Thank you very much, Krystian.